Great. So I think it should be okay now. And I'll present to you work about seasonal hydraulic plasticity in grapevine. Okay, it's the work of it's the PhD project of Jonathan Soret, which is a student in our lab. And I'll start from the beginning. I want to give a bit of introduction. I know some of you are really familiar with plant hydraulics and some of you are really not. So I'll start from the beginning, and the beginning of it all to me is the cohesion tension theory. Water in plants, they flow under tension, that is negative pressure. Water are capable of tensile forces, okay, because of the hydrogen bond, so the water molecules cohere to one another. And so whenever a water molecule leaves the stomata right here, so it pulls on another water molecule that pulls on another one and another one and another one. And so in a giant column of water molecule that extends from the leaf and down to the roots. And the cool thing about such a transport system is that it requires no energy. Okay, the plant doesn't have to invest any carbon or all kinds of photoassimilates. Actually, what drives this water transport system is the water potential difference between the soil, which is fairly wet, and the atmosphere, which is pretty dry. If you're in Israel right now, so you know the atmosphere is extremely dry. It says here minus 100 megapascal. I think we have about 300 in the last 4 days. But such a transport system, although it doesn't require energy from the plant, it does come with a set of problems, okay? Two of which I'll introduce to you now because they are part of our study. So one of them is that the plant requires positive pressure in the cell. So we said in the xylem there's tension, negative pressure. In the cell we have to maintain a positive pressure because it requires trigger for a lot of biological process, growth, cell expansion. And the way in which plants do that is they accumulate solutes. You can see right up here. I hope can you see my arrow, by the way? Yeah, because I'm sharing screen. So the water potential, it's the sum of the pressure potential and the solute potential, okay? So you can see that in the case, the water potential is at minus 1.5. If the plant accumulates a solute potential of -2, then it can maintain a positive pressure of half a megapascal. But if the plant is at -1.2 even and it accumulates a solute of -1.2, then the pressure potential is 0 and the plant loses turgor, and it has a lot of problems for the plant functionality. It doesn't really look like this. This picture is osmolysis doesn't really, I don't think it really occurs in plants, but the zero pressure can occur in plants, turgor loss, and it can even be probably negative pressure. So one problem of plants, they have to accumulate a lot of solutes to maintain dry conditions or to thrive under dry conditions. The other problem is xylem cavitation. And xylem cavitation is well, let's look at the phase diagram of water. So you know that water under atmospheric pressure in this room between 0 and 100 degrees, they are in a liquid phase. If you go under 100 degrees, you go to a solid phase, ice. Above 100 degrees, it's a vapor phase, right? It's a gas phase or vapor. But this is only true in this room under atmospheric condition. If we'll go to negative pressure, okay, or zero pressure or negative pressure, somewhere down here, or actually a lot lower, because we're not at zero pressure. We said plants are under tension. This tension can be minus atmosphere, -10 atmosphere, -50 atmospheres. Okay, so the water should long ago be vapor if we're thinking about energetic considerations. But the water are not, they are not in a gas phase. Sorry, I said the water should be vapor, right? I hope that's what I said. So the water from energetic consideration should be vapor, but they are in a gas phase because they are metastable. Okay, what is metastability? It's when there is some kind of energetic step that prevents the occurrences to go to the lowest energetic state. We do not go from a liquid phase to a gas phase, even though a gas phase is in a lower energetic stage, because there's an energetic step that requires some extra energy. In the case of the transformation from liquid to gas, it's the steric reorganization of the water molecules. So to reorganize the water molecules from liquid to gas would require additional energy, and that's why it doesn't happen. However, there are two scenarios in which cavitation will occur. One, if we take point number 2 and bring it down, like we will facilitate the cavitation by introducing all kinds of nucleation points, all kinds of impurities into the xylem, a grain of dust perhaps, or a blade. Like many people cut into the xylem because they need it for experimental reason. That will immediately cause cavitation. The other possibility is to take point number 1 and actually increase it in energy. When will that happen? If we dry the plant. If we dry the xylem further and further, at some point, point number 1 will exceed the energy of point number 2, and cavitation will occur. So cavitation does occur in plants. And I have here a very nice example from my friend and colleague, Alexander Ponomarenko. He took a thin slice of wood and he dried it. Okay, and because it was so thin, it was transparent. And while he was drying it, he was imaging it. And it's a super speed camera. And at some point he saw a cavitation event. You can see right here, a gas bubble appears and it spreads into the conduit. This is a conifer, so it's tracheids. Now, the reason we're studying this phenomena is because as soon as the conduit is full of gas, it's no longer conducts water. It breaks the water column and it loses conductivity. And if the plant will lose sufficient conductivity, eventually it will die. So many people try to quantify this loss of conductivity. It's what we call the xylem vulnerability curve. Okay, I'm not sure if you're actually seeing this as well. So it's the xylem vulnerability curve, and it describes the loss of conductivity as a function of the xylem water potential. So you can see that as the water potential goes down at 2 point something, 2.3 megapascal. For this specific example, we have a 12% loss of conductivity. It's what we call P12. At 3 megapascal, we have 50% loss of conductivity. It's what we call P50. I'm using these terms because I'm going to use them a lot. Okay? And at some point, I don't really know. It depends probably on species and environment, experimental conditions. But at some point, maybe at 50%, P50, maybe at P88, the plant will die because it will no longer be able to supply water to its leaves. So this is why we study this phenomena. And in fact, it hasn't been easy to study this phenomena because we are studying a metastable liquid. As soon as we try to manipulate it, it cavitates, it creates artificial cavitation. Okay, so if we put a blade into it, like we normally do to bring it to the lab, for example, we want to bring some patio, some shoots, some plants to the lab, we create cavitation. And therefore, in recent years, we are trying to use non-invasive method to visualize the embolism inside the plant. By the way, I'm using interchangeably the word embolism and the word cavitation. Cavitation is the transformation from liquid to gas. Embolism is what's in the gas-filled conduit. So it's pretty similar. Okay. So one of the non-invasive methods which we are using, and especially the one which we use in the lab because it's the cheapest, is the optical vulnerability technique. Okay, the optical vulnerability is a method in which we can visualize cavitation, the occurrence of cavitation. How do we do that? If you look into this gas bubble, this is an image from Hervé Cochard, and he's really zoomed in to the vein and he can see a gas bubble inside, okay? And this gas bubble appears to you as darker pixels. Why does it look like darker pixels? Maybe I can move that as well. Oh, yeah. Why does it look like darker pixels? It's because the light that is coming from the other side of the leaf is refracted, okay? When light is moving from a liquid phase to a gas phase or from gas phase to a liquid phase, it's refracted, it's changed its direction, and therefore less of it is coming to your eyes. So it appears as darker pixels. And what we are doing, not so zoomed in, we are looking on leaves And at some point, we see that the veins are becoming darker. You can see right here at the bottom an image and then an image after 2 minutes. And on this image, you can see that there is a thin, darker line on the vein. And that's because of cavitation. That's because gas bubble appeared in this vein. And if we resolve this using image analysis, you'll realize where is the cavitation and when the cavitation occurred, okay? So I have here cool examples of many leaves that I'm stuck. Okay, many leaves that I measured their cavitation or visualized the spread of cavitation in, this was done during my postdoc in the lab of Missy Holbrook. I don't know if you can hear the music. I have music on my computer. I'm not sure how if it's going through on Zoom, but what you can see is the time of the cavitation represented by the color. Blue color suggests cavitation occurred earlier. Yellow color suggests cavitation occurred later. And you can see when the cavitation occurred. Okay. So I hope you like this, but we didn't work not on any of these species. We worked on grapes. So I got a grape leaf drawing on the scanner, and you can see embolism as it propagates through the leaf veins. And you can see that also in a grape leaf, it starts from the major veins and propagate onwards to the minor veins. Okay. So now that we had this, method, we needed something to investigate it with it. And I'll start from presenting findings from my work still as a postdoc in the lab of Missy Holbrook. You can see here, this is the summary of 2 experiments, which we try to see what is the sequence of events during dehydration in potted grapes. So here you can see the stomal closure. First, we see some kind of stomal closure going from values of 4 bars down to 12 bars. So the plant regulated stomata to reduce the dehydration or to slow down the dehydration. Only afterwards, we saw some cavitation, wilting of the plant. What I write here is turgor loss point. And only after turgor loss point, we saw cavitation. Cavitation started at 1.4 megapascals, 1.5 megapascals, sometimes at 1.6 megapascal, okay? And based on these findings, so this is what I just said, stomal closure and wilting preceded the appearance of embolism. And based on these findings, we concluded that probably there's not substantial embolism in vineyards, okay? Because in vineyards, we don't really see turgor loss point. It's not very common for vineyards to wilt. I'm not saying it never happens, but it's not the common scenario. But I was challenged by one of our attendees of the seminar, my colleague and good friend, Ishai Netzel, who is a collaborator in this study. And basically, Ishai said, look, Ishai is a plant physiologist. He's measuring thousands of measurements of water potential. So he's very familiar with the water potentials of grapevines, especially in Israel, especially in our very dry and hot climate. And he's saying, look at your numbers. And the numbers don't lie, right? If you look at your vulnerability curve, so cavitation occurs at 1.4, 1.5, 1.6, 1.7. All of these values are values that occur in vineyards in Israel. It's not uncommon for a vineyard in Israel at the end of the season to be at minus 1.7 or even lower. This is one of his recent studies, and you can see these are 1, 2, and 3 are the stages of berry development. Harvest is toward the end, is the end of stage 3. So you can see that in the end of stage 3, some of his grapes reached minus 1.8. Okay, so according to the vulnerability curve I am showing here, there should be cavitation in these grapes. And in fact, other people that did vulnerability curves on in non-invasive method using micro-CT, MRI, and also the optical vulnerability suggested that grapes are even more vulnerable. They found their P50 sometimes to be at 1.4, 1.3, and even 1.2. Okay, so it seems like there is a lot of cavitation. The numbers don't lie, but my feeling was that the numbers do lie. Okay, and why am I saying that the numbers lie? It's just that this vulnerability curve, I don't think you can apply it to a vineyard in Israel. Why? First of all, this specific experiment I'm showing here was done in potted vines. And they are growing in very nice condition. These are in the growth chamber of Harvard, 25 degrees, irrigation every day. So probably they are less resilient to stress. Also, other people that using non-invasive method, micro-CT, etc. So they normally use potted vines because it's difficult to bring to your CT or to your MRI, or to bring your MRI to the vineyard. It's kind of impossible. Also, potted vines, they dehydrate really quickly. If you dry a plant in a pot, it dehydrates within within a day or a week or 2 weeks, really quickly, compared to a vineyard that dehydrates in 3 months, right? Or 4 months. You can look at this picture. Some of these vines got very little irrigation, and still it took them several months to dry. And during the time, the plant can acclimate. Plant has biological responses that if you allow them to acclimate, they will acclimate. And I have here an example, hydraulic example of turgor loss point. So this is data from the study of Maria Maralcina, and she took 8 different varieties. These are different varieties of grapevines. And she measured their turgor loss point in May, in July, in August, and September. So you can see in May it was about 1.2 for vines to lose turgor. In July it was 1.5 on average, give or take. In August it was 1.7. In September it was more than 2 megapascal, or lower than -2 megapascals. So these plants have acclimated substantially during the season. And this is not only her finding. Other people have found it in grapes, and other people have found it in other species. Plants can acclimate to their environment. And so accordingly, our hypothesis was, okay, that this is a Brendan Choate review. And let me move this again. So what you can see here is that this is water loss from stomata and caudicle. So you can see that as the plant dehydrates, okay, through dehydration, there's reduction in stomal conductance, okay? And until the point where we lose turgor, and cavitation starts only after we lose turgor. This is what I showed you earlier. The hypothesis of this study was that if we change turgor loss point throughout the experiment, we will also shift the stomal response curve throughout the experiment, and we will also see a shift in xylem vulnerability to cavitation. So that was the hypothesis. Everything should shift throughout the season, and that should enable the plant to maintain gas exchange while not losing turgor and not cavitating, despite the fact that seasonally in grapes, it's always that way. When they bud break, the conditions are much better than at harvest, okay, at the peak of summer. So what did we do? We went to Ishai's vineyard in Shiloh, and it's a Merlot vineyard. And what I'm showing you here, we measured all kinds of physiological parameters. I'm showing you only the treatment that was not irrigated. We have other treatments which I will show later, but now I'm showing you how non-irrigated grapes behaved. So you can see that in terms of leaf area index, there's, and the leaf area, the canopy is developed mostly in May, and then it maintains kind of stable. There are few new leaves that are growing in June and July, but not many. Most of it is growing in May. This is in terms of water potential. So in terms of water potential, you can see that the values went down from minus 0.4 megapascal early in the season to minus 1.3 later in the season. This is a stem water potential. If you're thinking about the pre-dawn water potential, it was about 1 bar early in the season and about 4 or 5 bars or 5 or 6 bars toward harvest. Now, we spoke earlier about acclimation or osmotic adjustment. So this is midday osmolality, and it increased dramatically throughout the season from 300 millimoles per kg and up to 700 millimoles per kg. Okay, it more than doubled itself throughout the experiment, kind of in agreement with what I showed you earlier. And because we had osmolality and we had the stem water potential, we also had elasticity. We did some pressure volume analysis, and we could calculate the turbo loss point. So this is the calculated turbo loss point, as you can see right here. It started from about 8 bars and ended up at minus 1.8 megapascal. So there was a shift of a whole megapascal throughout the season in terms of turbo loss point. So we were happy because we found at least the seasonal shift in turbo loss point. And now we wanted to see if there's also a seasonal shift in stomal response curve and in xylem vulnerability to cavitation. And clearly you cannot dry the vine in one specific day to see on that day what is the stomal response curve, how the stomata responds to dehydration on the 10th of May. It's not possible because it will take a few months to dry the vineyard. So we had to bring shoots to the lab. We did a lab dehydration trial at 3 points during the season. One was in the last couple of weeks of May, another was in the beginning of July, and another was in the end of August. Okay, what did we do in these dates? We brought shoots to the lab. Some of them were connected to a gas exchange system, okay, while they are drying, and some were connected to the imaging. This is some kind of a imaging clamp that allow us to see xylem vulnerability. We did it either with an imaging clamp or with a scanner. While these shoots were drying, we also harvested some leaves to see what is the water potential to be able to create the xylem vulnerability curve and the stomal response curve. Okay, so what did we find? These are the stomal response curve, the turbo loss point, and the xylem vulnerability curve in May. Okay, early season. So you can see that when you disconnect the shoot from the water reservoir, normally there is an increase actually in stomal conductance. It's what we call the wrong way response. Okay, there is a drop in epidermal turgor that opens the stomata, but quickly after the plant downregulate the stomata, and we see almost complete stomal closure near the turbo loss point, which is at 11 bars. Cavitation started only after. And I should point that these values are very similar to what I showed you earlier, okay, to the values I got from potted grapes. Turbo loss point at about 11, cavitation starts at about 14 or 15. You can see here, up here, this is the P12, it's 15 bars, the P50 is 18 bars. When we did the same trial again in July, everything shifted, okay, very coordinately shifted at about 3 bars. Stomal response curve shifted, turbo loss point shifted from 11 to 14. The xylem vulnerability shifted, look, it shifted the P12 shifting from 15 to 18, P50 from 18 to 21. Everything shifted by about 3 bars. And when we did it again in August, everything shifted by another 3 bars, okay, from 18 to 21 in P12, or from 21 to 25. Here it's 4 bars. Actually, the turbo loss point also shifted by about 4 bars. So it's a very coordinated response and complementary as well between all of these hydraulic traits. And to think about it, this is what I would expect from a Mediterranean species, especially a deciduous Mediterranean species, because the leaves are bud break when water is really available, and they don't really need to be tolerant to dehydration because there's no dehydration in the first few weeks of after bud break. But as the season progresses, they gotta be more and more resistant to dehydration, and they acclimate to it. Okay, and I should point that I'm showing you here again the non-irrigated treatment, but we had 2 other treatments. One of them was super irrigation, plants that were irrigated 24 hours a day. And the other is deficit irrigation, plants that got some irrigation. And you can see here that all of our treatments had high coordination between all of the hydraulic traits. This is the turbo loss points of all the different treatments, and this is the P12, and you can see a very nice regression. What we asked ourselves is if this shift, this seasonal coordination or this plasticity is caused by age, because through time the leaf basically mature, or because they acclimate to a different environment. Okay, if we change the environment with this change, if the plants would only be exposed to very highly irrigated conditions, would it not occur? And I think we have some answer to this question if you look at the clustering of the points. So the points are clustered by color. Color is the different dates. So all the points of May are kind of the same, are one near the other, and July are one near the other, and August one near the others. There's not much difference between the different treatments. SI is the super irrigation, DI is the deficit irrigation, and ANI is the non-irrigated plants. So there's not much difference between them, and I can show it to you, in another way. So this is the vulnerability curve of the different treatments. And generally speaking, we thought actually that probably the plants that will get less water will be more resistant to stress. And this was, in some cases, the result. You can see here that the red squares, this is the non-irrigated, are more resistant to cavitation compared with the other treatments. Also in August, the non-irrigated treatment is slightly more resistant to cavitation. But the truth is the differences were very small, less than 2 megapascal, and not significant in most cases. So we see a very substantial seasonal plasticity and very limited plasticity in response to the irrigation treatment. Okay, now perhaps the most complicated question would be what caused the differences in design vulnerability. Let me guess that we will spend a few more years trying to answer that. I'm not sure that the answer is so simple, but let me try. Okay, well, we did this year at least. So the immediate suspect are the differences in leaf structure, leaf morphology, leaf anatomy, and in grapes, leaves look very, very different. Okay, there is a growth pattern to grapes. Anybody that worked with grape is familiar with that. The leaves that are formed early in the season, and these are the leaves that were mature in May. We measured always the mature leaf, okay? But when we measured it in May, it's a basal leaf and a pretty large one. When we measure it in the end of the season, it's an apical leaf and a pretty small one, okay? And we always measured a leaf that finished their growth thanks to the very hard work of Jonathan with the help of Smadar, our lab manager, and Yossi, the field technician. So we knew when they finished growth. You see that the leaves that emerged early in the season, they grow to a substantial size and finish growth, but also the leaves in the end of the season, they finish their growth after about 4 to 5 weeks. It's not as if we kept the experiment, they would keep growing and ending up in a similar size to these basal leaves, okay? And when we compare these leaves, so you can see here that the leaves that are formed in May are about 3 times as large than the leaves of the end of the season. The leaves in May have about double the petiole diameter, and they have a substantially larger mean vessel diameter. We did cross sections with the help of Dr. Ilana Stein. And if you look at vessel distribution, you'll realize that leaves that are formed early in the season, the basal leaves, the large leaves, have also large vessel diameter. Substantial number of their vessels are larger than 30 microns, okay, all of this chunk. Whereas the leaves that are end of the season leaves don't have any vessels or nearly any vessels that are larger than 30 microns, okay? Now, if we think about cavitation, so what most people think of are the pit membrane thickness, and let me give you a short explanation to why, because I'm not sure everybody is familiar with the air seeding hypothesis. So what we're seeing here, this is the pit membrane. Okay, we're looking on the pit or the pit chamber. The pit is what connects two adjacent vessels, and the pit under normal condition is full of water. This is right here in the middle is the pit membrane. It's actually the primary cell wall. It's an area with no secondary cell wall. The secondary cell wall kind of separates and creates this chamber we're seeing here. And at some point, if one vessel cavitates, okay, then the liquid in it is transformed into gas, right? This is cavitation. and the pressure in it is atmospheric because gas is always at atmospheric pressure. On the other side, the adjacent vessel is still under negative tension, and therefore there is strong mechanical forces that are applying on the pit. Okay, and when these mechanical forces exceeds a certain threshold, a small gas bubble penetrates through the pit membrane and seeds the next cavitation. This is air seeding. And therefore, the mechanical forces in which the pit membrane is capable of, it's what determines the cavitation threshold. What water potential will lead to cavitation. And it has been hypothesized that the thicker the pit membranes, the stronger the mechanical force they can withstand. And Stephen Janssen group showed that there is a correlation across many species between the xylem embolism resistance and the intervessel pit membrane. The thicker the pit membrane, the lower the P50, okay? So based on this assumption, based on this assumption, we thought that probably late season leaves have thicker pit membranes. That was our hypothesis. So we sent our leaves to Stephen Janssen in Germany, and his lab analyzed these leaves for us. They use a transmission electron microscopy, and you can see images of the pit membrane. You can see on the right the image from August. Just to explain to you what you're watching, this is the pit chamber, okay, right here in the middle, and in the middle this is the pit membrane. This is the secondary cell wall. Okay, when we measured the thickness, and it's very clear to your eyes, so the pit membrane in August is about 1/2 as compared with the pit membrane in May. Exactly the opposite of what we expected. It's about 350 nanometers in August compared with 700 nanometers in May. And another thing that we found is that the pit membranes in August have a different electron density. You can see that it looks like a darker images. And probably it suggests that they have a different structure or different composition. We're not sure why. Stephen is investigating it, but they were very different in color. The pit membranes in May were very hard to identify even. They were, as you can see here, it's not so easy to realize where are the borders of this pit membrane. Now, when we did a regression between pit membrane thickness and vulnerability to cavitation, okay, you can see it here in the lower figure. We did find an agreement if we looked only on the leaves that were harvested in July and in August, okay? You can see that the thicker the pit membranes are, the more resistant they are to cavitation. This is their P12, and this is the pit membrane thickness. But if we also look in May, so the regression is completely destroyed. For some strange reason, the pit membranes of May, which is the blue color, is a lot thicker. If we look at Mies vessel diameter, there is a regression, a good correlation between P12 and mean vessel diameter. The larger the vessels, the more vulnerable they are to cavitation. I'm not sure if this is a real correlation, like it has some physiological base, or it's incidental, perhaps due to xylem collapse or something of that nature. Okay, now still there's a very important question yet to be asked, and this is, so did we have cavitation in the field? Okay, basically what I showed you is that the basal leaves were vulnerable to cavitation, right, or more vulnerable to cavitation, and the apical leaves less vulnerable to cavitation. So maybe by the end of the season, the basal leaves cavitated, right? That's a possibility. So one thing to answer that question, or one aspect, is the fact that there is a gradient of water potential within the shoot. The basal leaves are at, or the basal part of the stem is at -12 bars, whereas the apical part of the stem is at -13 bars. So the basal leaves are not exposed to as significant water potential as the apical leaves. And if we look at the vulnerability curve of the basal leaf, remember this is the leaf that I showed you earlier. It was measured it was formed, okay, on the 6th of May, and it was measurement by the end of May. And you can see that at 12 bars, there is hardly any cavitation in it. But still, because by the end of the season, we realized that the osmolality of both the basal leaves and apical leaves were exactly the same. If anything at all, the basal leaf had slightly more osmolytes than the apical leaves. So because their turbo loss point was kind of the same, we thought maybe also the vulnerability to cavitation shifted throughout the season. Okay, just like the same leaf, the basal leaf, accumulated osmolite throughout the season, maybe also its vulnerability to cavitation shifted throughout the season. And when we measured this same leaf exactly, right, it's a leaf we took from a very low nodal position. It's a leaf that we marked when it was formed. It was formed on the 6th of May, and then we measured it again in September. And it completely changed its vulnerability to cavitation. It became a lot more resistant to cavitation. And in fact, if you look at its vulnerability curve, it was more similar to the leaves that were formed later in the season. This is a leaf that was formed on the 22nd of July. And when we measured them both in the end of August or September, they were very similar in their vulnerability to cavitation. Okay? So it seems to us like there's no cavitation in these leaves, but we wanted before I'm going to another way to verify no cavitation, I want to take you back to the correlation I showed you earlier and to point out that what we're seeing as black squares, okay, these are the basal leaves that are that were formed early in the season, and we measured them in August, okay? So these leaves are marked in black, and you can see that they are on the correlation or on the regression of the pit membrane or the vessel size. You can see that they have shifted their pit membrane thickness. This is their pit membrane thickness when we measured them in May. This is their pit membrane thickness when we measured them in July. So pit membrane thickness is a dynamic thing, okay? I guess like many or most things in nature, but pit membrane thickness within the same leaf change its dimension and change also its electron density. So now I want to show you one more method which we use to verify that we don't have any vulnerability in the, or any xylem, or any xylem embolism in the vineyard. It's what we call the reverse optical vulnerability. We brought a leaf. So what is the optical vulnerability technique? I showed it to you earlier. It means that we bring a leaf to the lab and we dry it on the lab, and then we see that some of the pixels, due to light refraction, gas bubbles that create light refraction, are becoming darker. This is how we normally see cavitation. The optical vulnerability, the reversed optical vulnerability, is when we bring a leaf to the lab, and if it had cavitation, we see the exact opposite phenomena. How? We put it on the scanner, we image it, and then we flush out the gas bubbles by applying a strong positive pressure of water, okay, that flushes us out the gas bubbles, and then we image it again. So if there's no cavitation in that leaf, we expect the gray value from before flushing and the gray value from after flushing to be the same, and the embolism index would be 1 because we normalized one to the other, okay? And this is what we verified using a negative control. A negative control would be a shoot that we brought from the super irrigated treatment. It's again a vine that was irrigated 24 times a day, and therefore it maintained water potential at about 0.6 or 0.5 megapascal throughout the season, not water potential that anyone would argue that might cause cavitation. So that's our negative control, and you see that in fact it was at around 1, meaning there is no cavitation. Our positive control was bench dehydrated shoots that we brought to the lab and dehydrated to 2.2 megapascals, water potential that should result in cavitation according to all our vulnerability curves. And then we took the leaf, we put it on the scanner, imaged it, and then we flushed out the embolism, and we found that the pixels became brighter, okay, because there were gas bubbles there, and after flushing, they're no longer there. And you can see that the positive control had 7% increase in the transmittance of light. And when we tried the non-irrigated treatment in toward the end of the season, right? This is in the end of August and in the beginning of September. So these are the dates that we expect cavitation. These are the dates that we have the lowest stem water potential. We still found that the values are near 1, implying that there is no cavitation in those leaves. Okay, so this is what we did this season, and I want to give you some take-home messages. Oh, sorry, before that, I want to point out that it's not that I think that cavitation cannot occur in any vineyard at any time, and we are seeing some phenomena in the vineyards. Sometimes we call it vineyard collapse, where all the leaves are becoming dry and desiccated and then also necrotic. It happens very quickly, and this could be cavitation. It occurs normally in specific cultivars. It occurs normally in the end of the season when we have high resistance in the xylem due to other things but cavitation. The hydraulic conductivity of vines in the end of the season is substantially lower as compared with the early season. So I don't know for sure. I don't have evidence to tell you that this is cavitation, but we are working on it. And my point is, I'm not trying to imply that cavitation would never happen in a vineyard. I'm saying that it doesn't happen under normal conditions, not even in the end of the season, not even if your water potential is low. And this is the take-home message. Even if you see water potential that is at 18 bars, it doesn't necessarily mean that there is cavitation, despite the fact a lot of vulnerability curve would suggest that 18 bars should result in cavitation. And in general, to take a vulnerability curve that someone else did under different conditions and apply it to your study, I'm not sure it's the right thing to do. If you do it, you should do it with caution because it might lead to very wrong conclusions. Specifically in grapevines, late season leaves are more cavitation resistant. Let me guess, this is true for many species in the Mediterranean, especially deciduous species in the Mediterranean. And eventually hydraulic traits, stomal closure, tuber loss point, or xylem cavitation, they are all coordinated in a complementary way that enable plants, or at least grapevines, to maintain their stomata open toward the end of the season without losing turgor and without cavitating, without losing their hydraulic conductivity due to cavitation. So I want to thank the people that did this research. First of all, Jonathan Sorek. This is the PhD student that is conducting this study. And it was done with a lot of help from Smadar Grimston, our lab manager, and Yossi, our field technician. This is our collaborators, Dr. Ishai Netzel, Dr. Steven Johnson, and Dr. Ilana Stein. And I want to thank you all for listening. And if you have any questions, I'll be happy to take them.